Hi, my name is Andrew Morell, and today I'll be presenting about multi-arm post-docking spacecraft dynamics using penalty methods. I'd also like to introduce my co-authors, João Carneiro and Carneiro, who are colleagues of mine in the Autonomous Vehicle Systems Laboratory, and our advisor, Dr. Hans-Peter Schaub. So getting into the middle of that title, what is post-docking spacecraft dynamics? Also, I'll quickly define two of the acronyms that I'll be using throughout the presentation. The first being I or OSAM as in or on orbit servicing, assembly and manufacturing, which is kind of the category of mission that we hope to target with this work, as well as RPOD or RPOC being rendezvous, proximity operations, and docking or capture being the different phases of the type of mission that we are hoping to target with this work. So getting into these phases a little bit, we can think of rendezvous as maybe when we first launched our chaser vehicle into space, and it's maybe trying to match its orbit with the target vehicle. And eventually we get close enough that we consider them to be in proximity operations and switch our dynamics models to maybe a relative motion one. Then we get even closer and consider the spacecrafts to be in final approach, where maybe we switch from considering lining up the spacecraft's hubs relative to another to, if, as is increasingly the case, they have a robotic arm, trying to line up the end effector of the robotic arm of our chaser vehicle with the hub of the target vehicle. Now, eventually, after getting closer and closer, we achieve contact between the two spacecraft and have that moment of docking or capture where we need to introduce contact physics between the two spacecraft into our dynamical model. And if all of this goes well, we achieve a post-docked state of our spacecraft, now rigidly connected by one arm, or as will be the focus of this work, potentially connected by multiple arms. Now, while this is already a pretty high-level look at what the dynamics are involved with each of these phases of a mission, I want us to just think even a little bit higher level as to how we organize the dynamics of these different phases of a mission. Now, with the rendezvous and proximity operations, certainly no surprise to anyone that we consider the dynamics separate in this case, meaning that we have different equations of motion for each spacecraft that we're propagating independently. And even as they get closer and closer and even are touching each other, in this middle frame, we consider these also separate dynamics. There are forces being applied between the two spacecraft at that moment of contact between one another, but those are typically applied as external forces and torques to separate dynamical models with equations of motion as we try and resolve capture. Now, once we get to the post-docked system of spacecraft, what we historically see is that a single dynamical model is used for these, in which the combined properties of each individual vehicle are put together into one model with joint equations of motion and all this combined mass and inertia properties, as well as all the attached components of the individual vehicles. Now, while this may be advantageous for some cases or provide some level of simplicity, there is a relatively large amount of work, especially depending on the complexity of the independent vehicles, and putting together such a single spacecraft model that you then have to maintain as you make edits to the individual spacecraft models. And so what we'll be showing in this paper is a way of still considering the dynamics to be separate at this post-dock state, which I find advantageous for a number of reasons. One such being, if you think about the motion relative between the two spacecraft being so great that it would break your robotic arm, or whatever arm is connecting between the spacecraft, you'd like to know what these forces are going to be and predict that they're going to be too large and ideally let go of the target vehicle before a break of your arm results in ending the mission for servicing this satellite and any further ones down the road. You can also think of scenarios where a berthing maneuver is often performed, where when we initially grab onto the target vehicle, our robotic arm is relatively extended, but then we draw in the target vehicle closer to perform some amount of servicing on it. And then another situation that can be thought of is one in which the target vehicle is uncooperative for unintentional or intentional reasons. Now, also zooming in on our spacecraft, a set of two spacecraft that I showed in the last slide and will continue to show and manipulate throughout the presentation, we have our spacecraft 1, otherwise referred to as the chaser spacecraft, with its own local body fixed hub B1 and a connection point with the arm between the two spacecraft P1. Now, on the other side of this arm, we have the connection point on our spacecraft 2, otherwise referred to as the target, that point being P2, and it also has its own body fixed frame B2. Now, quickly looking at some of the prior constraint work that we've done in this area, we looked at specifically single arms between vehicles, and at the very start looked at a length constraint, wherein we said the distance between points P1 and P2, those connection points, needs to be fixed. However, no other constraints were applied. Therefore, both spacecraft could, as you could think, swivel around a spherical joint at those 2 points. And what we did to initially validate this work was we plotted all 4 points, both the hubs and connection points, in the B1 frame, which is what you see on the right side here, where because it's plotted in the V1 frame, we'll always see that the chaser spacecraft hub and its connection point are unmoving. But as this is a time history that we're plotting, we can see motion happening of the second spacecraft about spacecraft 1. So you see in the blue, the connection point on the second spacecraft swiveling around the connection point P1, in this case for a length constraint that's at a fixed distance, and then behind it trailing is the hub of spacecraft 2. What we did was started to increase the level of constraint to what we eventually called the direction constraint, where we fixed the joint at connection point P1. And as you can see, that allowed us to fix the connection point on the second spacecraft, P2, relative to our chaser vehicle, and eventually upgraded this to a rigid constraint in which, with a still time history plotted here of all points, they show being virtually rigidly attached to each other with no relative motion between the two spacecraft, which is our ultimate goal, to have full 6-degree of freedom rigid coupling between these two vehicles. Now, this was great that we got this to work and showed it some prior work for single arm docking. This is well applicable to some currently proposed missions, as you can see on the left hand of the slide, in the top left being NASA's OSAM-1 mission, and in the bottom left-hand corner being Starfish Space's Otter mission. Both of these have multi-degree of freedom Revolute robotic arms, I believe 7 degrees of freedom for NASA's OSAM-1 mission case. But on the right side, you see some of the multi-arm architectures that are being proposed that we wanted to start to fit this work to. Now, in the top right-hand corner, that's Astroscale's Lexi mission, which has 4 robotic arms. And in the bottom right-hand corner, also with 4 robotic arms, is ESA's bid at a in-orbit servicing mission, which is ClearSpace 1. Now, there's also an important distinction between the types of arms used here. On the left-hand side, those multi-degree of freedom Revolute robotic arms are relatively straightforward, but on the right-hand side with our multi-arm architectures, the 4 arms of Lexi have 1 rotational degree of freedom, thinking of it as a pin joint where it's attached to the hub of the spacecraft, but then those robotic arms can also telescope, so its 2nd degree of freedom is a translational one. And then for the ClearSpace 1 mission, in the bottom right-hand corner, those multi-degree freedom arms have all of their degrees of freedom aligned in the same axis, allowing the arms to wrap around the back of the spacecraft, but again, quite different from the single arm architectures where the degrees of freedom, the arms are strategically placed in different orthogonal axes of motion. Now, motivated by this, we decided to define new single arm constraint types to then combine. So the first of these was the sliding arm constraint, in which we define the connection point P2 on our target vehicle to move along a straight line relative to the connection point P1 on our chaser. Now, in the general way we formalize this, that line does not have to be coincident with the connection point P1. You can imagine if the telescoping linkage of your robotic arm was not the base linkage, this might be the case. However, for later work that will be showed in validating these, we did have that telescoping nature to pass through point P1, as is the case for the Lexi mission. And then on the right-hand side here, the second new constraint type we defined is a rotating arm constraint, where the point P2, that connection point, is defined to move along a planar circle relative to P1. And that's a fixed length circle, so the arm in this case is not telescoping, it's just similar to that Lexi spacecraft as a pin joint around the base. And of course, the goal here is to combine 2 or more of these to achieve a rigid coupling in the same way we saw with our eventual, what we call the rigid arm in the single arm work. Now, looking at the mathematics behind this, we formulate these constraints mathematically as holonomic constraints, just meaning that we express them as an equality set equal to 0 that is only dependent on the first order states of our spacecraft. In this case, those first order states being the position of the connection points P1 and P2. Now, for the length constraint in prior work, this was relatively simple, just saying that the magnitude of the vector between connection point P1 and connection point P2 must be equal to some constant r. Now, the direction constraint ended up looking relatively similar to this, but did so enforce this type of constraint, setting the vector between P1 and P2 equal to a constant for all 3 components of this vector when expressed in a certain frame. And after initially overshooting some of the complexity on expressing our sliding arm constraint, we figured out that this is actually the same as the direction constraint, but with strategically removing one of those 3 axial components that we are enforcing. And by expressing the vector between point P1 and P2 in a specific frame, we can have that length vector, depending on which axis we're releasing, be a specific direction that we want the arm to telescope about. And then finally, for the rotating constraint, what we did was express that vector between connection points P1 and P2 in spherical coordinates, and are always enforcing the radius along that circle. So that's the fixed length arm, but then choose either the azimuth or elevation angle to enforce and set equal to a fixed value, and let either the azimuth or elevation angle, whichever one isn't being constrained, be the free axis that the arm can rotate and swivel about. Now, how we actually apply these holonomic constraints to the spacecraft is through forces and torques, and we do that using a Lagrange multiplier method, in which we take the gradient of our constraint, which gives us, ensures that the direction of this force is only applied in such a way that it maintains the constraint to be satisfied, but doesn't apply any undue forces or torques on the spacecraft. And we scale that by a Lagrange multiplier, which you could technically solve for analytically, but would find yourself in just as difficult of a situation as analytically solving for a single spacecraft model. So what we instead do, inspired by the Baumgart stabilization method, is approximate this Lagrange multiplier using feedback gain methods. Now, in Baumgart stabilization work, that was done through a proportional derivative gain formulation, which you see in the left-hand side equation there. But we also expand this to use proportional, integral, and derivative gain formulations. And ultimately, we apply a torque to each spacecraft, just taking the cross of the distance between the hub and the arm connection point against the force that we're applying to the constraint. Looking at the validation and actual results of this, we first wanted to validate each individual arm type that is new to this work, the first being the sliding linear arm. In this case, we freed the axis in the y direction, and you see that relative motion plot similar to before, where this is a time history of the full 20 minutes, and as we'll always see, the hub B1 and its connection point P1 will not move as they're fixed in this frame, but we see that both the connection point on spacecraft 2, P2 in blue, as well as the hub B2 in green, are able to slide and slew about each other. Another way we look at validation of this is what is the orders of magnitude of constraint violations. Now, because we're expressing that Lagrange multiplier with feedback methods, we're not going to get perfect, but we can get very good, very small constraint violations, as you see in this case. So in both the X and Z directions, which we are constraining, we see on the order of maxing out at 10 to the minus 7th meters constraint violations. However, for the y-axis, we see that it's able to grow unbounded, which shows us that, yes, we're constraining our X and Z coordinate directions as we'd expect, but are releasing, as we intended, the y-axis. We see a very similar set of results for the sliding rotating arm, which showed us that it was working, where in this case, the elevation angle and radius are being enforced when expressing in spherical coordinates, but we allow the connection point on spacecraft 2 to move about a circle relative to P1. In this case, that circle is in the XZ plane. And we also see the azimuth angle in our constraint violations is the only term that's allowed to grow unbounded throughout our 20-minute simulation. Now we get to the work of combining 3 sets of these arms. So this is a set of 3 sliding arms. And once we connect them between, you see there's still 1 hub on each spacecraft in the relative motion plot, but now 3 connection arms. And what's plotted in constraint violations is the total magnitude for each individual arm's constraint violations being maintained below or around 10 to the minus 8th meters in this case, which is, depending on your level of simulation or how high fidelity you're seeking to have, it is quite good. And from a zoomed out view of the relative motion, we see that none of the connection points on spacecraft 2 or its hub are able to move about, showing that they are effectively fully fixed to each other in 6 degrees of freedom. And we see very similar results for the 3 rotating arms validation, where some angles or radiuses are able to get up to 10 to the minus 5th orders of magnitude, but for the most part stay below 10 to the minus 8th. Now, while this is all great for slow-moving spacecraft with no other external forces or torques applied to them, we wanted to start to stress test this a little bit. So what is seen on this slide here is first a translational maneuver applied to just the chaser vehicle. In this case, that is a constant thrust applied between minutes 5 and 8. And what that does is starts to tug the chaser spacecraft without applying this thrust to the target spacecraft. And what we're hoping to see is small constraint violations mean that these constraint forces are maintaining a rigid coupling between our 2 spacecraft and making sure that the target vehicle is also pulled along with our chaser. And we see that when we start this thrust, we jump up to greater than 10 to the minus 4th order of magnitude constraint violations. And then similarly, when we do a rotational maneuver and torque the spacecraft, we also jump up immediately in orders of magnitude of our constraint violations, which depending on the fidelity that you're seeking at this point, may be permissible. Maybe you need to increase your gains to drive those down and not let it grow as high. But then rather interesting, you can see after the thrust is finished applying or after the rotational maneuver is finished, we don't necessarily go down to the same pre-steady state constraint violations that we saw. And that's because often we are in a more excited state once we get past the end of the actual force or torque being applied to the spacecraft. Meaning that if the client and target vehicle are moving about their common center of mass, spinning about their common center of mass, that's going to be stressing the constraint between them a little bit more and requiring or maybe creating slightly larger constraint violations. Now, in conclusion, we've seen that we can achieve virtually rigid coupling between individual spacecraft models using this multiple constraint arm formulation by just specifically releasing individual degrees of freedom of the component arms. This holonomic constraint formulation method is agnostic to the component vehicle, so it doesn't matter how many solar panels or reaction wheels or fuel tanks you have on the individual vehicles. It's relatively simple to just apply these external forces and torques between a specific point on each vehicle. And it's also agnostic to what simulation architecture you want to use this in, considering that the addition of external forces and torques, or at least generalized ones, is a very common capability to any simulation framework for spacecraft. Now, one of the drawbacks is that gain tuning requires careful consideration, considering factors such as the size of vehicles, how quickly you're maneuvering them, as was shown in the last slide, as well as maybe the length of your arms, as all these contribute to how great of a force or torque the individual spacecrafts are going to experience. And so you can see those proportional and derivative terms, or potentially also an integral gain term for our Lagrange multiplier, need to be considered carefully depending on how maneuverable or vehicle size you're going to be using, such that you have appropriate orders of magnitude constraint violations for the stage of or fidelity of work you're seeking to do. And then lastly, this can achieve very high computational efficiency, the greater constraint violations you're willing to accept. However, once you step down to extremely small constraint violations in very dynamic situations, you may run into slightly higher simulation times. Next steps for this work are all the previous work shown in this presentation is results shown from that lab, which use very simplified spacecraft. But in the Autonomous Vehicle Systems Laboratory, we have the Basilisk simulation framework, which is a very high fidelity simulation framework that we want to use in this because it allows us to plug and play already existing component models, such as flexing solar panels and other time-varying geometries, such as floshing fuel tanks, so that we can do also in our next steps here, stress testing of these multi-arm constraints. We did something similar for our single arm constraints where we applied different time-varying geometries to the individual spacecraft to see how the constraint violations were able to keep up, and also applied more complex maneuvers to each spacecraft. So with that concludes this presentation, and thank you for watching.